Hello students, this is Dr. Faizan Mirza. Here in this video, I'll be covering the basic working definitions and the basic statistical tests and what you need to remember regarding this and how to use these. Obviously, that needs time and practice, which we'll be doing gradually. So initially, what these terms mean, this is what we'll be discussing. You need to remember these definitions because they are these definitions and not just stating them in as it is in the golden words, but also utilizing the concept behind that definition and how that particularly is utilized in setting up an experiment or in analysis, evaluation, or drawing conclusion. So starting off, control experiment. What exactly is a control experiment? A control experiment is basically an experiment in which the factor which you are investigating, the independent variable, is absent. So already discussed with you, independent variable is the cause. So you repeat an experiment without the cause. You just subtract out the cause from the experiment. So the experiment becomes a standard for comparison with an experiment in which the cause is there, because the cause will bring about a change in the effect. So independent variable is the cause and the dependent variable is the effect. Prediction, this is a statement about what you think might happen, a guesswork based on prior understanding and underlying hypothesis. Hypothesis, yes, hypothesis will be a statement which provides an expression of prediction based on a body of prior knowledge and testable by an experiment. Normally, you will be asked to devise an hypothesis. When you are devising a hypothesis, you will always start to state there is a significant dash dash between the variables which you are saying. You basically try to make a statement saying that yes, a correlation or the difference or whatever the link between these variables, it exists. You agree that it exists and the effect is significant. So this is how you make your hypothesis. But at the same time, when you're asked to make a null hypothesis, the null hypothesis is a statement saying that there is no significant association or difference between two sets of data. This association is the same thing that you are discussing in hypothesis. And in the hypothesis, you basically say there is a significant association. Now, this association could be the association between the means of the data or the correlation or between observed and expected or something which we'll be discussing in other videos. Data can either be nominal data or ordinal data. Nominal data is a set of qualitative data. Qualitative means something that is either present or which is absent, something which is yes or no. So this data can be categorized and this data cannot be arranged in sequence. It is assigned distinct categories. So categoric data is called the nominal data. Ordinal data, on the other hand, ordinal data is one that you can order it, which you can rank. It will be a set of qualitative data. All the values are not numerical, but the individual results can be arranged in a sequence. Now coming to continuous data and the discontinuous data. Continuous data means a set of quantitative data. This is quantitative, something which is numerical, something which is having dealing with numbers. And this dealing with numbers, which will be of any individual region, can have any value between the two extremes. So that's continuous data. And whenever we are having continuous data, we can calculate mean out of that data because we know that all the values can be added up and divided by the total number of values to get the mean. Discontinuous data, on the other hand, is also called discrete data. It is a set of qualitative data in which each measurement can belong to a limited number of values. For example, when we're discussing phenotypes, we know 9331 ratio. The 9331 ratio is when two dihybrid organisms are crossed and their genes are not showing any kind of linkage. There is no epistasis going on, there is no sex linkage going on, there is no autosomal linkage going on. We see four different phenotypes in the ratio of 9331. The data that we collect is discontinuous data because one phenotype lies in the category or a particular quality. They have the phenotype which is 9 of 16 and the others are 3 at 3 each, and then there is 1. So that's discontinuous data. So moving on, normal distribution. Normal distribution is a set of data in which the graph shows symmetrical distribution around the mean value. It will be a bell-shaped curve where mean will be equal to median and it may be equal to mode as well, but that depends. So mode, what is mode? Mode is also known as the modal class in which the most common value is there in the set of results. Median is the middle value of all the values in the data. You have studied mean, mode, median previously in your previous statistical classes back in your O-level previous standards. Standard deviation. A standard deviation is a calculated value that indicates the spread of data around the mean value. The standard deviation shows to you whether the the data is less varied or more varied. If the value of standard deviation is low, it means that the data is less varied, the data is more reliable. If the value of standard deviation is high, it means that the data is more varied and less reliable. This is the formula to calculate standard deviation. We take summation of this whole we take the square root of this entire calculated value. This includes summation of x minus x bar whole bracket squared divided by n minus 1. We'll be using this in calculation later on, so I'll discuss it later, how this formula is used. Although I've covered standard deviation in my videos in biodiversity classification and conservation, where we have covered how standard deviation is calculated for some petals there. These two curves, they show how normal distribution curve are there. So normal distribution curve will always have a central value. It will be equally dispersed on both sides. The extremes will be low in population, and the central value will be the most frequent one. So this is how the normal distribution curves actually are shown. There's a term that you keep in mind, 95% confidence interval. Now, before we follow what 95% confidence interval mean, we need to follow what standard error. Standard error is a calculation that indicates how close that calculated mean value is likely to be to the true mean value. True mean value means the true population mean. It is denoted by SE or SM. Either this SE or SM is basically you calculate standard error by dividing the standard deviation with the square root of small n. Small s is the sample size or the number of the values that you have counted. Now, standard error value can be computed and multiplied by 2 to get 95% confidence interval. What's 95% confidence interval? It is a range of values calculated as the mean plus minus twice the standard error. You can get 95% certain, you can be 95% certain that the true value of the mean lies within the range. So for example, if I'm asked to calculate 95% confidence interval, I'll compute the value of standard error, I'll multiply it by 2. So for example, my standard error value was 0.2. So what I'll do, I'll just multiply 2 by 0.2 and I'll get 0.4. So 0.4 will be written as plus minus 0.4. The confidence interval is 0. Minus plus minus 0.4 plus minus mean. So whatever the mean is, for example, my mean is 7.84. My 95% confidence interval is 0.4. So this value tells me that my mean value is 7.84. It may be above by 0.4 or it can go below by 0.4. And the true mean of that population lies within this range. And I'm 95% certain that yes, it lies within the range that I have calculated. So that's 95% confidence for you. Error bars are a line which draw through plotted point at the top of the bar on graph extending two standard errors above and below to the mean value, indicating the point on the bar. You can be 95% whether the true value lies within the range indicated by the error bar. So what do you do? Again, you just plot the value of error bars here, and this is what you do. You have two bar charts here, and this is the error bar. The error bar is plus minus twice the standard error. So you calculate, you just highlight it this way by making the error bars here. So this error bar shows to you the true mean value of the population lies here. And although this is the calculated mean, the value that I got here is the calculated mean, and the error bar shows me the true mean range, and I'm 95% confident that the range lies here. Now, then what we can do, if the error bars are there and drawn, what we can do next, we can just see whether the overlap is there between the error bars or not. The lower limit of one error bar and the upper limit of the other error bars can be seen whether they have an overlap or not. Now, if they have an overlap, if the error bars are overlapping, it means that the difference between the two readings is not significant. If the error bars do not overlap, for example, if error bar was here, the other was here, and we start to see the upper and the lower limit, and we see there is no overlap. No overlap of error bar means that the difference between these two sets of data is significant. Hardy-Weinberg principle should be recalled, how we calculate P plus Q is equals to 1, how P squared 2 Q square 1 can be done using an equilibrium, the Hardy-Weinberg equilibrium. P square represent the homozygous dominant population. Both alleles together, 2PQ represent heterozygous dominant population. Q square represent homozygous recessive in the population. Whereas single P represents the single dominant allele, single Q represents the single recessive allele. How we need to do that? You may be given the values in percentages or in numbers. When given in numbers, this means you are provided the frequency. For example, if you are told 8 in 50 individuals have small p, they have recessive alleles. So this is the frequency provided to you. So in these questions, normally Q square is provided to you in the form of frequency. And when it's frequency, it means it will provide it to you in this case that 8 in 50 or 12 in every 1,000, something like that. Or you may be provided a Q square value as a percentage, for example, 18%. Now, if it's provided 18%, what you need to do, 18% need to be converted to frequency by 18 upon 100, because 18% means that every 18 in 100 will have that particular condition. So you can be provided the value of Q square in either way. What do? You can just see, for example, 5 rat out of 80 are white guinea pig, calculate the homozygous dominant, heterozygous dominant black guinea pig in this population. You have Q square, which means 5 out of 80. So 5 out of 80 will give you the frequency, which is 0.063. And then you can convert it to percentage if you want. Then single recessive allele is calculated by taking the square root of this, because Q square is this. So you place the value of Q square here. Q is calculated by taking the square root of this. You get your answer 0.25. So this is single Q value, a single recessive allele, which means 25%. Now the single recessive allele can then be computed in our first equation of Hardy-Weinberg principle, and we can calculate P out of it. We can just take the value of Q there and subtract it from 1. In this case, we get 0.75. So it means 0.75 is the frequency and 75% is the percentage of the single dominant allele P. Now, if I want to calculate the dominant in population, what I'll do, I'll just do P square, which means 0.75 taken squared. I'll get the answer 0.563, which means 56.3%. I may be asked heterozygous dominant in the population. Heterozygous dominant is always calculated as 2PQ. What do? You multiply the value of P and the value of Q that you have already calculated with 2. And the multiple of these is actually your heterozygous in the population, which comes out to be 37.5. So Hardy-Weinberg principle questions normally come, and the statistical tests that they normally ask you are Ttest and chi-square test and Pearson linear correlation and Spearman rank correlation. You may be asked about hypothesis and null hypothesis. Hypothesis will always be a statement agreement between the variables. You say that yes, the association is there and the association is significant. Null hypothesis will always be that the difference between or the association is not significant. So, and then if it may be association, it may be correlation or the difference between observed and expected, or anything according to the question. T-test. Now there are 4 kind of statistical tests which you should be knowing, because every time they give you a question in P5, they always have one of these in the paper. So you should be very thorough with how these are calculated and what actually is the reason why a particular statistical test is being used. So for example, if you are using T-test, T-test is used when you want to know if 2 sets of continuous data are significantly different from one another. Already mentioned to you, continuous data means you can calculate means. So the 2 sets of data are the ones you will have 2 means, one of first set of the data and a mean of the second set of the data. 2 sets of continuous data is there, mean of both are being compared. More than 10 readings of each set should be provided, and both are following normal distribution. They have a similar standard deviation. This is the formula that you use. The formulas will be provided to you in the paper. You should know how to compute and how to just find the answer. Wherever you have bar mentioned, for example, X bar, X1 bar, X2 bar, 1 and 2 represents the first set of data or the second set of data. All variables here are the first set of data. This is all the second set of data. So bar here represents mean. So X bar means the X bar 1 means that you are taking data from the first set and it's the mean. S1 is the standard deviation, you square it, and N1 is your number of samples total in that particular case. The same goes for the second set of data as well. You compute the values and you calculate the answer. The answer that you calculate normally actually tells you what your calculated t-value will be. You calculate the t-value, and once the t-value is calculated, you will compare it against a critical value. For example, if I I start to carry out testing, or you can say I have a prediction that the nerve conduction velocity, mean nerve conduction velocities of the ulnar nerve control the movement of your fingers. of the gamers is significantly different from non-gamers. So this is, I'm saying that the association is there. So this is the hypothesis. So if I have to test this hypothesis, what I'll do, I'll take some gamers and some non-gamers. For example, I'll take 20 gamers and 20 non-gamers, and I'll see their nerve conduction velocities using the electrodes. There's apparatus that can be used for that. I'll have the nerve conduction velocities of the non-gamers and the gamers. What I can do, I can just calculate the mean for the non-gamers and the mean for gamers. What is the mean ulnar velocity of gamers and mean ulnar velocity of the non-gamers? I have two means now. I'll calculate the standard deviations for both. I know my sample number is 20, 20 each. So I'll compute my values and I'll get my T. So once the T value is calculated, the next you do is find out the critical value. The critical value is taken from the table, and the critical value will always be taken for p less than 0.05. 0.05 probability tells you that you are 95% sure that the conclusion that you will state is actually what's correct. And you are leaving 5% chance of error, 1 in 20 chance of error. Degrees of freedom will have to be calculated, and degree of freedom for t-test is calculated with the formula of n minus 1 plus n minus 1. So in this case, my degree of freedom would be 20 minus 1 plus 20 minus 1, which actually gives me 19 here plus 19 here. I'll add them and I'll get my answer, and that is like 38. So this is my degree of freedom. So that's how degree of freedoms are calculated. Once I have my critical value, I'll have my critical value from the table. I'll just compare it with my calculated t value, and I'll see whether my t value is greater than the critical value or not. If my t value is greater than the critical value, it means that the difference in the mean is significant and it's not due to chance. And gaming is causing this change because it's all about cause and effect. Gaming is the cause which caused the effect that yes, the nerve conduction velocity was faster. Now, for example, if my t value was smaller than the critical value, in this case, the difference in the mean would not be significant, and my conclusion would be that the difference between the means is not significant. It's only due to chance, and this is because the t value is smaller than the critical value. And I'm 95% sure, and I'm leaving 1 in 20 chance of error. When you're using chi-square test, chi-square test is used to know if observed and expected results are significantly different from one or not. You have quantitative data, nominal data, and which must be discontinuous. Discontinuously, it will be in separate categories. For example, ratios will be provided to you. You know when you get 1:1, 1:1, 1:1 ratio. You should know when you get 9:3:3:1 ratio, and you should know how to calculate the expected values. I've already discussed this in my videos in inherited chain chapter. So again, you have a chi-squared calculated value. You compare it against a critical value for p less than 0.05 or probability greater than 0.05. Again, the same thing goes, the calculated chi-squared value, if it is greater than the critical value, which means that the difference between the observed and expected is significant and not merely due to chance. So, and this maybe you should recall independent assortment, sex linkage, autosomal linkage, epistasis, because these are the main kind of questions that come. But again, chi-square test can be applied not only to genetics but to any other situation as well. For example, if you want to study the effect of pollution or the effect of how the grazing has affected a particular land, again, chi-square can be used. It's not just limited to this genetics. Pearson linear correlation. There are two types of correlation that you study in your syllabus: Pearson linear correlation and Spearman rank correlation coefficient. Now, Pearson linear correlation, actually you calculate the value of R, and the value of R is calculated using the formula summation x y. You subtract the value of n, x bar, y bar. X bar, y bar are the means of the two sets of data. You divide it by n minus 1. And again is the number of samples that you have, the number of readings. You subtract 1 from it, and you have Sx, Sy. Sx is the standard deviation of the set X, and Sy is the standard deviation of the set Y. You have the value of R, and the value of R that you get, you just compare it with the range of -1 to 0 to +1, and you will say whether the correlation is significant or positive, or significant negative, or it's a weak correlation, or it's a strong correlation, linear correlation, because Pearson is always just linear correlation. So what do we have here? It is used when you want to know if there is a linear correlation between two sets of paired of data. The data will be continuous. The data will be in two sets. You will have at least 5 pairs of data. The data will be paired. You will have paired data here in Pearson correlation. The scatter plot will be drawn, and the scatter plot suggests that there might be a linear correlation because you can actually see, you make judgment by eye. You judge by eye, you make judgment by eye that yes, the correlation appears to be there. Both set of the data show normal distribution, which mean mode, median are all equal. So what do you do? Your value of +1, 0, and -1 can be there. If it's close to +1, indicates a strong positive linear correlation. If it's around 0, it indicates no linear correlation. If it's around -1, it means there is a strong negative linear correlation. We move on to Spearman rank correlation coefficient. Now, when you're calculating Spearman's rank correlation coefficient, you calculate the value of RS. RS is calculated using the formula RS is equal to 1. You subtract this whole from 1. This is 6 multiplied by summation of D square. Do just keep in mind this D square is not the D of diversity index. Diversity index, Simpson diversity index is, we also calculate D there, but there the D that we calculate there is the coefficient of diversity of Simpson index of diversity. It's not this D which we are using here. So there are two separate D's in your syllabus, although the symbol is same, but they mean something very different. So when you're using Spearman rank correlation coefficient, we have you use the formula 6 multiplied by summation D square divided by N cube minus N. Again, all the formulas will be provided to you. You should know how to use the formula. Now, whenever you are using the formula, you will always solve this bracket first. You will apply the rule of Bodmer's for any calculation which is provided to you, because this is the basics of math. This is the basic thing in math. You follow Bodmer's there and you calculate the value of RS. Again, the value of RS will be between -0, 0, and +1. Accordingly, you can state whether the correlation is there or strong or negative or positive correlation is there. When do we apply Spearman rank correlation coefficient? It is basically when you want to know if there is a correlation or not necessarily linear between two pairs of sets of data. The correlation seems to be there, but the correlation is not necessarily linear, so we can't apply Pearson correlation. Again, you will have quantitative data that can be ranked. This is the first of the ranking data that we are discussing. We have not discussed ranked data in any of the other statistical tests. The data is not following normal distribution. The random samples are for each data are collected, at least 5 pair of data. The scatter plot suggests that yes, the relationship might be there, but not necessarily linear. It cannot be used at the point of scatter plot shows you a positive correlation and some show negative correlation. It means the graph is U-shaped graph. You can't apply this formula. Now, whenever the answer will come, again, as I told you, you will calculate between RS value of +1, -1, and 0, but you may be provided with the critical value table. Now, if the critical value table is provided to you, you will just compare the value according to the critical value. And again, you will just see whether your RS value is greater than the critical value or not. For example, the critical value that I find from the table is greater, is actually smaller. My RS is greater. So for example, my RS comes out to be 6.08 and my critical value is 4.01. So my RS value is greater than the critical value. What kind of conclusion will it be? I'll say that yes, it means that there is a significant correlation between the paired data which I have just studied, between the variables that I have studied, and yes, a strong correlation exists there because the RS value is greater than the critical value. But for example, if my critical value was 6.08 and my critical value was for example 10.8, 10.82, for example. In this case, my RS value is smaller than the critical value. If my RS value is smaller than the critical value, it means that the correlation is not significant. It's merely due to chance. So that's what you do. You should know how to compare this. And again, one more thing which I'll be discussing, the use of negative and the positive sign in RS or in the Pearson correlation. It's important because you should not ignore this. Eventually, your answer may come to be -0.93 or it may come 0.93. In both cases, the first value means a positive correlation, the second means a negative correlation. So you cannot ignore the negative sign here. If the negative sign shows in the calculation, you mention it in the answer. So that's pretty much it from my side. That's all. I hope the video was helpful for you. Thank you so much.